let's talk about categorical cross entropy loss, and it's building on the binary cross entropy loss that we apply to the problem of generative adversarial network. And when we apply the binary classification loss to discriminant, because discriminated data output is a binary output. Is it real? Is it fake? And for CNN, and one of the most popular application when it was invented is for object recognition. So there's classification, there are multiple classes. And it's also in supervised training setup in that we need training labels. So a bunch of images, and we like to assign labels to different animals, different object, different vehicles, and so on. And so, for instance, let's consider this particular example that we have three classes, and suppose we have this stack of network, then eventually, if the output layer output this particular shape, so we have three classes. Let's use C and to denote with three classes or three categories, 1, 2, 3. And in our training set with a batch of 4 examples, so we use I to index over my batch. So 1, 2, 3, 4. And also this is output logic. And we haven't applied the final activation function yet. And if we like it to be for classification, we like it to be some probability distribution. And we talked about how we can use softmax and to achieve this. And softmax, the equation is that, so we have take each element, so we raise to the east power e to the x. And then in this case, I used z, so I used e to the z and index over the classes, like this class, and then also sum over the 3 classes. Okay, and then we'll be able to get the distribution in this vertical form, and they will supposed to add out to 1 for the proper distribution. And now I'm going to just delete this and delete one of this, and hopefully I could reproduce my my calculation. So what I'm doing is that I'm going to do exp to raise to the z's power. So it's like this, select a column, and then I'm going to sum over ex. Again, we'll repeat this. So they will give me softmax value, okay? Now, so let's say the softmax gives us a prediction across 3 different categories, and we would like the target distribution to be at the ground truth based on the labels we provided earlier. So the target I like to write in y hat. And so let's think about if what are the labels? Let's just give some labels, say use a different color to denote my labels. I somehow looked at data, I think this is class 1, class 1, class 2, class 3. And what would be the ideal distribution, knowing that the first example is supposed to be class 1, that we want to head 1, 0, 0. And second will be 1, 0, 0. And third is the labels 2, so I want the second category to be 1 and 0, 0. So this is my target. I like the network eventually after applying softmax to produce this number. So let's just analyze, let's erase this and analyze this, how it's doing. So 0, so for this one, for first example, I like it to be 1 for first position, but my first position actually is 0.21. It's not great. I like this to be sort of going in the opposite direction. I like it to move up close to 1. Whereas for this position, I like it to move down. 0.58 is too high. I would like to move down. And the loss function that allows us to achieve that is cross entropy. And in this case, a multi-category, so categorical categorical cross entropy which is the extension of binary class entropy. So the equation is going to be y hat times log prediction. And then so we will consider one example at a time. With 4 examples in my batch. So one example at a time. So for first example, I equals 1. We like this to be index over my class labels 1, 2, 3, go in this direction. And then we like I to be 1. So so I sum them up. So there'll be the cross entropy loss for that particular example. If I run this from I to my fourth example, 1, 2, 3, 4. So I have another index I, and it allows me to index through on the other direction for my examples. So earlier we looked at the equation for binary classification is a special case of this one. For binary, C is equal, even though it equals 2, but because when you have two classes, when your class 1 is 0, 1, but class 2 must be 0, 9.9. So if the second probability for the second class is implied in a situation like this. So and that simplified into the form we looked at earlier. But anyway, so this is how it can be implemented. So this made me just and another important thing is going to be negative, so that will go in the direction we want. We want the loss function to give us a value that the smaller it is, the better that we want. Okay, so negative will give us that direction. So this is going to implement this y hat. For this is I'm going to have a matrix for individual. So I'm going to let's say minus y hat is this times this element wise multiplication times log. I want to use log base e. So I use ln for log base e. And I'm going up to select my prediction, which is my p. Okay. So that's gives me my cross entropy loss at the individual position in my matrix here. And then we add them together, sum, then we get a total entropy loss. All right. So they have this number called 591A1014. So about 5-ish. And I could, before I move on, I can go out and play with just as a sanity check that earlier on, I liked my first class to be class 1. I'm sorry, first training example to be class 1. And if you should look at the raw score, you already know it's not doing well. It's just 1. But whereas the raw score for class 2 is higher. So say, and so I would expect that if I increase this value, it will bring me closer to what I want. As a result, the cross entropy loss should go down. So let's do the experiment. If I add it to 10, which is much higher number, I would expect this 5.9 to go down. And if this is happening, it means that it's doing well. So one feature that it would be kind of nice to play with is that I could use formula, and there's a code watch window. So I could say I can add the watch to this particular cell, which is my loss. So I have this value code here. Can I draw it? Can I make it bigger? No, I can't. Okay, so here's some small values and move down over here. And then if I go up here, so if I move this up to 10, I'll expect this value to go down because the loss is reduced. Let's see what is happening. Okay, yeah, it goes down to 4, right? And then for this case, 2, 3, 1 is still not ideal. If I change to 10, it should go down further. And this one, so second class, it'll move down to 10, go down further. And third, it move up to 10 for the third class, and the losses become smaller and smaller. So I'm going to undo this. So for now, can I undo this? So I can restore to where we are and not loss going up again. So let's do the experiment another way. Suppose somehow this value goes up. The second class, the score for the second class goes up. Okay, but we know the first example supposed to be the class 1. As you can see that the loss value goes up 13 instead of 5. So this is something that we can experiment. This is following the logic and intuition that we want the cross entropy loss to behave. And I also prepare another experiment down here that I'd like to compare the differences between two epochs. And if I would add this to add some value that I control, I would like to be able to not only move the direction, but also by the amount of a gradient that I want to compute. Gradient tells you, if you take a little step in your logic, in the score, how much that difference will be in terms of the loss value, magnitude of the loss. So that's what the gradient tell you. And interestingly, if you combine this equation of your softmax, you see this e to the z power, And there's also a law kind of bring it back, somehow cancel out, and some kind of interesting math. Eventually, you have this very simple expression that I just love to see this expression of prediction minus target, which is my y hat, which is now give us a gradient, which is a loss gradient with respect to logic, which is kind of important is respect to logic, because this right before logic is where before logic raise to the e and bring it down to log n base e. Maybe just write this here to just to emphasize we need base e in order to sort of inverse back to where it is. Eventually, we have this very simple equation which is to give us a gradient. And we saw that this is the third time we see this equation. So in the L2 loss, we see this equation. And in the sigmoid, the binary cross entropy, when they combine, you see this equation. For cross entropy in the categorical case today, you see this equation again. And then we might see this a couple more times down the road. Every time there's a loss function, you might wonder why we have to add this log? Why do we have this mathematical equation? Turns out in deep learning, we all like to eventually get to this particular simple form for my initial gradient. And then we'll do backpropagation later after this section. Okay, so let's implement this. How can we implement this? I'm going to take prediction, go back up to select my prediction P, and simply minus, actually, sorry, let me do it one more time. Let's do an equal sign, go up here, I'll select my prediction matrix, and now I'm going to minus my target matrix here, and that'll be my gradient. So what does it mean? So I have 0.8, meaning that if it goes up, the loss goes down. We ran exactly the experiment. We raise 1 to 10 over here. And then expect the loss goes down just because we know we expect the first example to be the first class. And then the other two has a negative, in the opposite direction. So if you ever raise the score for the other two, you expect the loss to go up, okay? So this sign sort of like tells us a story of where the ground truth labels are for each of these examples. And then 0.8 tells you the magnitude, 8 times, 0.8 times. If you go score go up by 10, and then 10 times 0.08 is 8. So you should expect the loss to go down by 8 because the negative sign here. So it tells you what it is. So I have this set up that I just going to add a little, suppose after the one training epoch once move to 1 to 2, I have some changes to logic, DZ, and this I try to simulate that. Suppose we have, right now it's no change, and I use the same equation to calculate a new prediction, the same y hat, but new prediction y prime, and then same equation, and then a new loss y prime, but then we have a difference between the new loss and the old loss. This value tells us how much loss it has changed as a result of changes in the logic. And now it's 0 because there's no change. So going back down here, so if go up by 1, we're likely to go down by 0.8, but it's usually not gonna be the case. Let's say it go up by 1, they go back down here. It's actually 0.68. Why is that the case? It's because the step is a bit too big. So gradient is only work when in the very locally when you take a very tiny step. So if I take a tiny step at 0.01, so hopefully I should be able to see something at 0.8. 0.008. Let's go down and see the case. Okay, 0.0078. It's kind of close enough. Okay, but I know you kind of get it. And so in reality, there will be a lot of changes like this. Suppose we have this one is minus 0.01. Suppose it moved in a different direction, and now expect this two to cancel out because they have the same amount of gradient. But because first example pull in one direction, second example pull the other direction, as an end result, it could get a very small change in your loss. So that's how the impact of different example in the batch my pull the gradient in a different direction. But overall, when you have lots of training examples and over a many epoch, eventually find the general direction, they just move your model to the right place that to produce the result you want. Okay, so hopefully this is a very comprehensive breakdown of what usually a very difficult topic of cross entropy loss. It seems to be usually black box. They just apply set that as a parameter in your PyTorch code. But hopefully with this example, you say concrete number to see the behavior of why we design the loss function to be like that, how it gives us very simple form of calculating gradient and so on. All right. So with that, now we are ready to talk about backpropagation. We know how to kick off the backpropagation process by computing the initial gradient with that take that little difference. So I prepared this backpropagation worked out examples to show you how we can actually do that. And we looked at this example in the autoencoder case. Only one thing is kind of new that we have not seen before is Maxpool. How do you backpropagate through Maxpool? We're gonna see that today. And all right, so this kind of map out what we want to do at the abstraction level. They just reviewed what we have here. We have a very simple convolutional neural net that we have follow this pattern with input image, and we have turned into column form, so we know we're running some kind of window. So there's this window, and with two of this, and then eventually two filters here, H1, H2, and get us two feature map down here, and then we wrap them back into feature map, and then we run this in another window with 2x2 window and get this in columns and run Maxpool, and then wrap it again and flatten and do a final output projection to get my size we want. We see softmax with 3 elements. So it tells you that it is a 3-class categorical, classification problems, and have a target tells us that for this example, batch in particular example here, we have a very simple case with just one example. So target 1, meaning that I'd like this, the label for this example is 1, first class. And then categorical cross entropy loss already calculated here and total loss. But what I kind of leave it blank, so when we calculate, remember how to calculate this? What is the equation? It's y hat is here, and p is here. And then so the equation is going to be p minus y hat. And to implement this, I'm just going to select my p. So you just can, once you know this, it's just cannot believe how easy it is to start cross backpropagation. Now I have this initial gradient. Okay, now I'm going to use trace my backpropagation computation graph kind of in a backward. So we know this is going to be the loss, partial derivative of loss with respect to, if I write P is this is a common mistake, should be the logit. Okay, remember right before logit, you have this softmax raised to the E and come back down to your target. Then you have kind of log base E, this thing. Okay, so that's how you kind of eventually have this simple form. And then if I move up to over here, I usually like to move up over here and to move to my backpropagation portion that I added to my multi-layer perceptron. So in this case, I just copy this. So this is what I just have. And then, so if we look at this, so this is my Z logic. How was it computed? It's going to be the weight. And so we have this flattened, let's say call it H hidden value. So it's WH, and I just ignore the bias. Let's just add bias. And with that, we know that this is my W, and Z, the partial derivative of W times H. So it's the opposite. H turns out to be W. Okay, and if you have this two form, so just move it down here a little bit because I think I'm blocking where I want to multiply, just move down here a bit. Okay, now we have this two, and then you realize if you will multiply these two terms together in this way, you're going to cancel out your z term, and you get the loss, partial derivative loss over h, and you have this term, then you can keep propagating up, and then and similarly, so we have h here. What is h? H turns out to be the other direction, the other side of w, z over w. If you multiply these two, I arrange in such a way that you can actually visualize this. It's going to be z is the one canceled out, and you end up with the loss and with respect to weight. And this is very important for gradient descent. If you would apply gradient descent, this is the amount you would multiply with the learning rate, and then you minus, subtract this, subtract that from your previous way over here. You subtract this one, this thing. You subtract, you take this and you subtract the learning rate times this gradient, and you'll be able to get a new weight for the next step. Okay, now we're gonna propagate further up. So we have this h, but then reshape back to 2D, and I can propagate this. This is the same, and going to be, this is the same as well. I don't know why this is not showing. Oh, okay, maybe I should implement this. So this is going to be match. I can refer to over here, but I need to add a transpose. I forgot to add a transpose, but I just like this first. Now I add transpose. So if you add this transpose, the shape is going to match magically in this arrangement. And now I have this. Now I have this one. I can go back here because I write it upside down. So I'm going to select this one first, and then I select this one next for my maximum allocation. Then I will be able to get this. Okay, this gradient, loss gradient, they could propagate upward. And so this one, because in this arrangement, I already transpose, I could just multiply. Come on. Multiply, select my first matrix here, and select my second matrix here. Okay, it's not doing the right one. And select my second matrix down here. And then the result of this multiplication give me nicely the loss gradient with respect to the weights. And then this one usually doesn't propagate any further. So this is something you just used for gradient descent. And this is the thing that you propagate upward, and in order to keep repeating the same process. But now this is a new area that we are gonna. So remember, this came from this flattened value as output of Maxpool. So we'll consider this Maxpool. So this is the same value, h, a different shape. And this is the window coming from earlier. Let's just call it A from the activation from previous layer. And they're this is a window version of this, sliding window version of this, with column format version of this. And with Maxpool, the way that we propagate gradient is that we need to remember during the forward pass, the indices that are selected to have the maximum response. So what does it mean? So we have this value, the feature map we looked at before. Suppose we have the indices across every single location in the feature map. So I have used this red represent 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 18. When we convert them unfold them into this column format. So these are indices kind of distribute. So you can see I check whether it's correct. So for my first window, it's 1, 2, 4, 5. And I have this window, 14, and it should be correspond to this window, 14, 15, 17, 18. Seem to make sense, right? These two windows to check. Okay. And then eventually, so we select, so this one is 3, 4. So this is index. We keep track of that where the maximum value is. So this is 1 to 6. Okay, I should, can't really see it. This is actually not correct. I don't know why. It's supposed to be 2. This number, but it says here. But this is correct, 8, 8. 8, 8, 8, 8. But this is not correct, I think. Maybe I need to, I don't know why. Maybe the implementation is not correct. Let's see. Is it correct? Oh, this one. Okay, there's a bot there, but that my goal, this is supposed to be give me 2 because it's in this index. Just say, okay, let's just leave it there. But for now, we know where this gradient come from, so we can just go from here. Let's use my red to say that we have this gradient coming from earlier 0 minus 0.2. And because I remember it comes from pixel number 4, and pixel number 4, according to my map, oh, I see. Okay. Anyway, my pixel number 4 is going to be over here. So they propagate over to this location. And then says, look at another one. There were 2 of this blue one. They're both pointing to pixel location number 8. So, and then if you look at this map, 8 is over here. So it corresponds to this location. So these 2 fall over here. And when we add these 2 together, you get minus 0.4. Okay. And then just one more. Let's do one more. Maybe here. Go back to red. Where does this go? Where does this gradient go? Then this is 18. Where's 18? 18 is here. So let's go back to here. So there's 0.42. And this things all make sense. Now we have collected all the gradient from down here, and then we'll then reshape into this. Now ready to propagate further upstream. So this is my the loss respect to my feature map here, A, that collected all the gradient coming from the pixels that have pixel location or feature location that have maximum responses that was left, that passed through Maxpool. And now we have this ready to use. And how can we keep moving up? So this is A, then we shape back to here, and we're not using it. And so, and for ReLU, and what the ReLU, it's now gonna have a local gradient here. So suppose that B, this is B. And B respect to A, the local gradient basically, if you are above 1, the gradient is 1. If you're below, sorry, if you're above 0, gradient is 1. If you below 0, gradient is 0, nothing in between. So you can just map this. So 2 become 1. So here you can see this 2, 0, 2 gonna map to 0, 1. So that is this mapping. Okay, so once we have that, then we multiply these 2 together. What do we get if you multiply these 2 together? What got canceled out? A got canceled out, right? And you will end up having here. That's how we can continue this propagation. And so let's just do this, code this up. So I want to be able to do an element-wise multiplication between my A, which is this one, A over B, and then select my second matrix, which is L over A, and then this gives me L over B, except that it doesn't let me. Oh, I see. So I have to actually do this times. This is element-wise multiplication. So now we can continue this backpropagation. So let's consider if we have a weight here. Now this is actually already I with images, okay? Just a reshaped form of the image I. So this is WI plus B. Okay, that's how we obtain B earlier during the forward pass. And similarly, we could do this loss with respect to, sorry, not loss, B over what is B, what is W is B over I. And what is I? I is going to be B over W, kind of opposite. Okay, so now we can set this up. And then with that, then we're ready to do multiplication. So we have multiplied these 2, what do we get? Multiply these 2, what do we get? Which one get canceled? B got canceled. What do we left with? L over I. And what do we need this? We usually do not quite need this until we continue to propagate upward. And since we already reached the input, so usually we just don't compute this, but we do want to have this one. How do you compute this one? So we'll multiply these two. If we multiply these two, B over W and L over B, which one gets canceled out? B gets canceled out. What do we left with? Loss over W, and which is what we need here. Let's just say as simple as maximum application of all this across different window location. And the reason is that all this window location contribute to some kind of gradient. Pull your loss function in a different direction, hopefully in the same direction. So you over a batch. So maximum application, and then select here. All right. Yes, I cannot select this. Let's select this down here. Okay, select this one. My second matrix here. Ta-da. So I now have finally computed this one. Okay, so and with this, let me zoom out a little bit. How can we continue? So next step is that we'll take this weight, two of this, and then take this weight gradients and multiply with a learning rate, and then you don't add to the original weight. Instead, it's opposite. You subtract this value from your original weight, and you'll be able to get new weights, and you continue this process. Okay, so we won't work out the gradient descent for CNN, but I just want you to use this as an opportunity to go through backpropagation one more time. So, and then also see how we do something differently for the Maxpool. It will reverse pulling our gradient back to where it should fixed location that contribute to the gradient. So that's the way that backpropagation work for convolutional neural network. Okay. All right. Before I wrapped up convolutional neural network lecture, I would like to highlight certain takeaway. And I'll say the first takeaway is that convolutional neural network is a neural network. So if you zoom out and some of the examples we saw earlier, that it just looks like a neural network MLP structure. You have this ways, and you multiply maximum application, and you have this Maxpool, probably something new. But you have seen Maxpool before in the 2D filter lecture. Even before deep learning, we could already see how you could apply filters based on this. The key is to be able to represent that into a matrix representation by turning your image input into column format. So that's like a key. Then you'll be able to run this in parallel instead of doing the hard thing of running CPU cycle by cycle. You can use maximum application unit like GPU and to perform all the maximum application at very few clock cycles. And then it becomes possible to brute force to figure out your weights. So second takeaway is that in the convolutional network, you no longer handcraft the filters. So these are being learned by the network through backpropagation and gradient descent. Whereas in the 2D filter lecture earlier this semester, we looked at Laplacian filter, we looked at mean filter, we looked at Gaussian filter. Each one of them has some mathematical equation that underneath describe its shape, and then we use theory, we prove that it could actually capture some differences. And then you might remember when we actually did that, there are some parameters we have to choose, like what will be the Gaussian. For Gaussian, what is the spread? How big is we should pick for the standard deviation, and so on and so forth. And which takes a lot of trial and error. What is the size of Gaussian filter? That, for instance, and even for Laplacian, there are some parameters as well. Back to convolutional neural network. As long as you set it up with the right labels and training examples and categorical cross entropy loss, and then you figure out a way to represent that into matrices, you give them to GPU, and it can just brute force and to figure out all the weights for you, and that could solve the particular problem that you like it to solve.